let's discuss reactions of anhydrides. We'll see that they're interesting, but possibly less useful than chlorides for reasons we'll get into. One way to industrially produce an anhydride is to react acetic acid with itself under quite harsh conditions, 800 degrees Celsius, and we can basically drive off water to produce the anhydride. And this is how acetic anhydride is produced in industry. It is the most common anhydride. It doesn't work as well for other anhydrides. Another way to make anhydrides would be to start with the acid chloride with one R group on it and react the carboxylate anion of another carboxylic acid that has a different R group, and that would occur as a nucleophilic acyl substitution. We lose chloride as a leaving group, same mechanism as we've discussed before, and we'd end up with what we'd call an asymmetric anhydride. And actually I should probably use unsymmetrical. Asymmetric has a different connotation in organic chemistry. And so we have a way to make an unsymmetric anhydride. As far as the reactions of anhydrides go, very similar to acid chlorides. They have similar reactivity, similar reactions with various nucleophiles. Just that the leaving group now, of course, is this piece. So it's a little bigger than a chloride, which actually causes more waste. So we're losing half of our molecule when we react this in a nucleophilic substitution reaction. So it's oftentimes better to use the acid chloride. And let's say we wanted to add a methyl acyl group, and I chose to use this unsymmetrical anhydride for some reason, and I'm reacting that with this weak nucleophile. There's really equal probability of our nucleophile attacking either of those carbonyl species, and you can see that that will give us a mixture of products, and maybe my desired product involves adding that group to my alcohol, but I'm going to get a mixture, so it's not really an efficient reaction. So that's why it's probably better to use the acid chloride. The leaving group is smaller, there's less waste, and there's only one acyl group to attack. These molecules do have their uses. Let's look at one practical use of acetic anhydride. If we take salicylic acid, which looks like this, and we react it with acetic anhydride, we will acylate the phenol to make aspirin. So acetic anhydride does have its uses in industry, and most likely when the chemist who's running this reaction is finished, he or she will collect the byproduct given off, the carboxylate leaving group, and reform acetic anhydride from that, so that can be recycled. Another useful bit of anhydrides comes in the form of cyclic anhydrides. We could take succinic acid, which is shown here, it's a 5-carbon diacid, and if we subject it to high temperatures, we can get it to cyclize, lose water, and create this 5-carbon cyclic anhydride. And if we choose to react our cyclic anhydride with some random alcohol, we could end up with a product that looks like this. We acylate the alcohol, but of course the leaving group is still attached to our molecule, and so we've broken open the ring. After we work this up with acid, mild acid, we should be able to get a carboxylic acid on the other end. And so a cyclic anhydride, such as shown here, is a great way to add 2 functional groups to our molecule. We started off, we took this alcohol, we acylated it with one of the acyl groups here, making this new bond, and then we protonate the pendant carboxylate group. We end up with a carboxylic acid next to, a few carbons away from, our newly formed ester group. So Cyclic anhydrides do have uses just as acetic anhydride does. Really, that's probably the only common uses of anhydrides that are common in industry.